Now that we've looked at polarity of molecules and the different shapes that molecules can make, what we're going to do is talk about valence bond theory. We're going to talk about how the atoms actually bond together to explain why the shapes that we see are involved. And so it's a combination of Lewis structures and Vesper, the valence shell electron repulsion theory, and how this all works together. What we're really going to do is we're going to talk about how in the world does that central atom have the ability to accept an electron and what orbitals are involved. And so normally you think of the reactions occurring around the valence electrons, and the valence electrons are those electrons that are the s and the p's. And in most cases, that's all that's going to occur, but we did see violation of octet in some of our structures, and there were more than 4 things bound, meaning that there were more than 8 electrons bound. And so we're going to see what happens when that occurs. Now, what we need to do is we need to talk about what a covalent bond really is. And remember, I told you that the covalent bond that we had was 2 atoms that were competing, atom A and atom B. They were each competing for an electron. And so if the electrons are directly in the middle, it's pure covalent. And if they were over towards the side, the bond was a little bit polar. We normally would write the bond like this with a line between representing 2 electrons. But if it is polar, we're going to say one side's a little bit negative, this side's a little bit negative, and this side's a little bit positive, and we have a polar bond. Now, what this line represents is a sharing of these 2 electrons between A and B, whether it's pure sharing, equal sharing, or even unequal sharing. And so what happens is, when you take a look at 2 atoms coming together, you're going to see the 2 hydrogen atoms, the s orbitals are involved, and they will come towards each other, and then there is a place where there is an overlap of the regions where the electrons live, and in this overlap is where the bond actually occurs, the pairing. And that overlap really represents the bond between 2 atoms, and we usually draw a line. Now, how close can these 2 atoms get to make this bond? We can have a distance, and if the 2 atoms are too far apart, they're not bound. There's no bond that is going on. But the problem is, if you get them too close, the nuclei start to repel each other, okay? And so if by chance you start getting them close and you have overlap, you start to have stability because of the 2 electron pairs sharing. You get to a perfect area in which the electrons have a lot of area to share. The 2 nuclei are far enough apart that the repulsion is not involved and not competing. But if you push the 2 atoms even closer together, we're going to make it such that it's not going to be favorable. And so there is a bond distance between 2 atoms. Every bond distance is different, in which it maximizes the area where we make the bond. Now, this overlap that is between these 2 atoms directly is called a sigma bond. A sigma bond. And we represent that again, remember, by using a line, a single line. Now, when we want to bind other atoms to a central atom, what we have to do is we have to know that, or we have to actually share electrons between the 2 atoms that we're looking at. And so if I take a look here at beryllium, beryllium has in it a electron configuration of, it looks like helium, and it has a 2s2 electrons. Now, I'm going to write it in a different way in this electron Lewis structure itself than what I would normally, because what I would say normally is beryllium is 1 electron, 2 electrons, and I'm just going to write it such that I have 1 on one side and 1 on the other. But also, if I look at beryllium and I write the electron configuration differently, I would have helium and 2s. I would actually say that those electrons are paired. Okay? Now, if the electrons are already paired in beryllium, then if I have something coming in, I don't have a place for an electron pair to bind to the beryllium. If my organization of the electrons are in the way that I taught you as in the atom, but this is the elemental form, not the form that happens when a reaction occurs. And when a reaction occurs, what we're going to get is a change in how the electrons are treated around that central atom. And so, if I look at this Lewis structure, I can articulate it such that the beryllium each provides 2 valence electrons. The fluorines themselves provide 7 valence electrons, and when I put them together, there's a bond between 1, 2, 3, 4, 5, 6 lone pairs. And if I actually do the formal charge, beryllium brings in 2. I assign it 1 and 2. 2 minus 2 is 0. For the fluorine, 7. Count how many I have in the structure. 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. And this side looks exactly like the other. This is a true good Lewis structure, although the beryllium does violate octet. It is less than octet, but formal charge allows me to do that. Now, let's take a look and see what happens with the orbitals. What we're going to do is, here is the electron configuration of beryllium. Here is where all 4 electrons are at. Now, here's the problem. I have no place to pair an electron. So what I'm going to do first is I'm going to promote in the reaction one of the electrons from the 2s to the 2p section. Then I have a place where an electron can come in and pair to this one, and an electron can come in and pair to this one. Now, the problem with this is when I mix these or hybridize these, what I'm going to do is actually do part of the chemical reaction. I'm going to change what those orbitals look like. Now here's the s orbital, a sphere, just like we talked about, and a p orbital. One of them is a dumbbell. We tested you on that. You had to know what the shapes were for each. But what I'm going to do is I'm going to mix these two, and I'm going to place an electron in each one. Now, when I mix an s and a p, I'm hybridizing or mixing those orbitals. And what happens is the shape that they once were, a sphere and a dumbbell, okay, get changed into a very large dumbbell on one side and a very tiny dumbbell on the other, and a very large dumbbell on one side and a very tiny dumbbell on the other. What you don't see when I put them together is there's the little tiny dumbbell and there's the little tiny dumbbell on the other side. And what happens is the best arrangement that these can have is that around the central atom, I have one big dumbbell where electrons can share and one big dumbbell where electrons can share. Now remember, I mixed it so that I can put one electron in one space and one electron in the other space, such that I can now have an overlap with an electron coming in here and an electron coming in right over here. So I have a bonding. And so when you promote these, I haven't touched the 1s, and I have left 2 p's by themselves, but I have mixed together 1s and 2p and 1p, so that I have 2 spaces, so that electrons can come in. And the F will have electrons, one of them on one side will come in and bond to the other, 1 electron from fluorine, 1 electron from beryllium. And so between the fluoride and the beryllium, And between the fluoride and beryllium, I will have a bonding pair. We will write that just like this. Those single bonds, where the electrons are shared between the two atoms, that sigma bond is represented by the one line bond. Now, this is what it would look like. I have 2 electrons in the 2s in the ground state, in the elemental state. But when I react, I mix one of the s and one of the p's and put 2 electrons in, and the 2 electrons, one each from chloride, will come in and create the bond and will make and fulfill the octet around the chlorines by taking the 1 electron from beryllium on each side. And so we have the bond between the beryllium and the chloride and the beryllium and the chloride. They have 2p orbitals that have nothing, and so the 2p orbitals were not mixed, were not changed, they are just sitting there available. Okay, but to bond 2 things, I had to mix 1 s and 1 p to make a new hybrid orbital called an sp. In this case, the angle between this is 180 degrees. It is linear. For the sp2 hybridized system, where I'm going to take and I'm going to promote 1 electron up into the p's so that I could have 1, 2, 3 spaces so that 3 bonds can be formed, I'm going to take 2 of the p's and 1 of the s and hybridize them or mix them into a new arrangement called sp2, so that 1, 2, 3 entities or atoms can donate 1 electron and create a pair, create a bonding pair, create a bonding pair. 1 p is left alone. An example of that would be boron, who brings in 3 electrons from its ground state. Fluorines each will have 7, 1 non-bonded pair, 1 lone pair of electron, 1 lone electron, and those 2 will come together, form a bond, those 2 will form a bond, and these 2 will form a bond, as you can see down below. But let's take a look and see what that might look in 3 dimensions. Okay, the boron atom has 2s completely filled and 1 in the p. That is its elemental form. At this point in time, unless I mix them, I could only bond 1 thing coming in. But when I mix those, 1 s and 2 p's, I get 3 spaces in which 1 electron can live from the central atom, and then 1 electron can be donated by each atom coming in. So this is what it would look like in the elemental form before the reaction, but as soon as it reacts, I'm going to mix 2 s's and 2 p's to create 1 large lobe, 1 small lobe, and when the large lobes are placed in there, the best arrangement is to make it trigonal planar. This is why we have the trigonal planar, and each of those shared electrons between the atoms is represented by a single bond or by a sigma bond. For sp3 hybrid systems, that is a central atom that is bound to 4 things or that can accommodate 4 bonds. An example of that would be the element carbon. The electron configuration has 4 electrons, 2 unpaired in the p orbital, 1 paired in the s orbital. But what I'm going to have to do is have 4 separate spaces in which electrons can have a pair coming in. So I'm going to promote 1 of the s into the p. 1, 2, 3, 4 single electrons. But when I mix, this is part of the reaction, I hybridize, creating 4 separate large lobed, 1 small lobe. I'll have 4 of them, and then I'll put them all together. An example of this, if we take a look and see what that would look like, the carbon would have a full s with 2 electrons. It would then have 1 in the p and 2 in the p, with 1 p empty. I'm going to promote and mix or react those orbitals together to create 4 spaces in which bonds can be formed, and that is called an sp3 hybridized. Here are the 4 electrons, 2 in the s and 2 in the p in the ground state before it is reacted. When it completely reacts, all of those are mixed, and the best arrangement is a tetrahedral. And as the electrons from each of the hydrogens in this case come together, creates a overlap and a sharing of electrons between the carbons and the hydrogens, the angle of this tetrahedral will be 109.5. Now, you get into items that bond more than 4. You violate octet. You put more than 8 electrons around. And we said valence electrons were only s and p. That is true as long as we obey octet. When we violate octet, what we have to do is mix another orbital. Well, if I've used all the s and I used all the p, the next orbital available are d's. D electrons can sometimes be reactive. We normally think that they are core electrons, but under extreme conditions, D's electrons can be reactive. And so to have 5 bonds around a central atom, what you're going to have to do is promote electrons from the s, you take all of the s and all of the p and 1 orbital in the d, okay? And what you do is you mix 5 different orbitals, 1 s, 1, 2, 3 p's, and 1 d. So if you have 5 things bound, that's going to be trigonal bipyramidal or trigonal bipyramidal. And to get 5 spaces, you have to mix these orbitals, an s, 3 p's, and a d, to get the arrangement that you need. Octahedral requires you to mix 1 s, 3 p's, and 2 d's. So, very simply, if you have a linear arrangement, you have to have 2 binding spaces. I have to mix 2 orbitals. I mix an s and a p. It's called an sp hybridized system. If you have 3 things that are bound, or 3 electron domains where electrons have to live, then you have to have 3 orbitals mixed, 1 s and 2 p's. If you have 4 spaces in which electrons need to have a domain, then you will mix 1 s, 1, 2, 3 p's together. This fulfills octet. If by chance you need 5 spaces, you mix 1 s, 1, 2, 3 p's, and then add 1 of the d's to create enough spaces for bonds to be created. And if you have 6 electron domains where you're going to create bonds, what you're going to have to do is you're going to have to mix 1 s, 1, 2, 3 p's. You've used all your p's, so then you're going to have to add 1, 2 d's to create the hybridized system that allows for 6 bonds to occur. So, as long as you know what the electron configuration is, the electron pair geometry, then if it's linear, it's sp. Trigonal planar, sp2. Tetrahedral, sp3. Trigonal bipyramidal, sp3d. And octahedral, sp3d2. Very simple in terms of as long as you know what the electron pair geometry is, you can then identify which hybridization it is. Now, sigma bonds, the single bonds that hold everything together, here's the sigma, a lowercase, it is the electron overlap that is directly between 2 atoms. These are the electrons that they are tugging and pulling and holding on, both of them that hold the atoms together. That is a sigma bond. This is not the only way that you can bond. There is what's called a pi bond. A pi bond is the second bond in a double bond and the second and third bond in a triple bond. So if you have 2 bonds between carbon, then you have 1 sigma bond and 1 pi bond. If you have a triple bond, then you have 1 sigma bond and 2 what are called pi bonds. Now, what's the difference between a pi bond? The sigma bond is a direct overlap and represented by one line. So it's a direct overlap of electrons between the atoms represented by a single line. The pi bonds are made where an electron can jump back and forth between the two atoms through the p orbitals. And so what it looks like is the p orbitals will overlap. There will be an overlapping where electrons live. What it looks like is this stretched out, excuse me, this electrons can jump between the pi orbitals above and below the atoms. Now that's the difference. The sharing of electrons are above and below for pi bonds, and the sigma bond is directly between. How would that look? All right, here is the very complicated look about how this system would be put together. A carbon that has a hydrogen, a double bond to carbon. 1, 2, 3 electron domains. 3 electron domains is sp2 hybridized for 1, 2, 3. Okay, this would be 120, that would be 120, that would be 120. Centered around this would be trigonal planar, and we see trigonal planar. I've mixed an S and 2 P's, but I have 1 P left over. This double bond is represented by electrons that are in this P that are shared back and forth. And I can see that here. This double bond is easy to draw. This one is harder to draw, and this one's even harder to draw to show where all of the electrons are. But let's take a look at what it would look like. And you can see the overlap above and below. Now what's interesting about a double bond is that you cannot twist the molecule, because if you rotate one against the other, what you're going to do is you're going to break that sharing. So the double bond places constraints on the structure. Single bonds can rotate around. You'll learn that a lot more about that consequence in organic chemistry. A triple bond, we can see in the triple bond, we can label this. This is a sigma bond held. Sigma bond represented right here, atom, atom, and this overlap, that's a sigma bond. And a sigma bond here, atom, center, the overlap here. And one sigma bond for the carbon, where the overlap of the electrons is between this and that. But then we have 2 pi bonds, pi bond, represented by a sharing of electrons above and below, that's a pi bond, and sharing of electrons in front and behind. If we actually smeared them out, you would lose, you couldn't see the sigma bond between the 2 carbons, but there is sharing on the top and bottom, and a sharing in front and back. Now the electrons can either be on the top, the electron pair can be on the top, the electron pair can be on the bottom, they can't be on both at the same time. So that is a triple bond. Now, remember when you write resonance structures, okay? And so here's a resonance structure for the ion, the nitrate ion. When we draw these structures out, the difference, there is no difference between this first, the second, and the third. All of these are represented. Now, what we know is when we place it in an instrument to measure the distance between the nitrogen and oxygen in the single bond, and the nitrogen and oxygen in the double bond, we know that single bonds are longer than double bonds. And so when we measure this, we do not see this. We do not see 2 long bonds and 1 short bond. What we see is that this double bond could be in any position, and really what it is rotating between those positions at all times. And so what really would be the best drawing of this structure would be this, where I would put a dotted line saying that the double bond is, and that pi bond is rotating between all of these, because when I place this into an instrument, I get a bond length between oxygen and nitrogen, 3 same distances, which is not as long as a single bond, but not as short as a double bond. Each bond has a double bond character. Okay? What it would be like is drawing it this way, in which one of the bonds is shown as a double bond in one direction, but really it can jump this way and it can jump that way. It is partially jumping all the time and partially in any one of these. We call this jumping back and forth between these areas delocalized. They're not localized in one place, they are delocalized amongst many. The pi bonds, the double and triple bonds, have the ability to be delocalized. An example is benzene ring. The benzene is held together by single bonds between the carbons, so 1 single bond, 2 single bonds, 3 single bonds, 4, 5 single bonds, and 6 single bonds, okay, represented by these lines. The second line are the bonds between the pi bonds, and so in one case they could be shared here and here, and they could be shared there and there, and they could be shared there and there. But just as easily, they could be shared there and there, and here and here, and here and here. Which one is happening? In actual cases, they are happening all at the same time. Instead of a dotted line, we're going to use a circle. In this particular case, showing that the bonding can be all the way through. And so the delocalization is important. And in this particular case, it actually brings stability that is a higher stability or a lower energy state than either of the two before. And so when you do Lewis structures, okay, you must determine how many electrons each are contributing, draw the Lewis structure. And then you will go back and you will create, you will count how many electron domains are around. And remember, you count them. A non-bonding pair is one domain, a single bond is one domain, and multiple bonds, double and triple bonds, count as one domain. If you have 2 linear, 3 trigonal planar, 4 tetrahedral, 5 trigonal bipyramidal, and 6 octahedral. Once you've placed all of the atoms and all of the non-bonding pairs into that shape, then you get to the molecular geometry. Okay, that molecular geometry does not consider where the non-bonding pairs are. It only considers where the actual atoms are. The atoms are influenced and placed in positions because the non-bonding pairs are there, but the non-bonding pairs cannot be seen. You can be asked for the bond angles that are represented. You can be asked for the hybridization, and if it is a polar molecule. Now, the fact that polarity, you have to determine, are the bonds polar? If the bonds are polar, then maybe it could be a polar molecule. But if the bonds are polar and they are canceling each other out or pulling on every side of the shape, then you can have a non-polar molecule that has polar bonds. And then you can count the number of sigma and pi bonds. So sulfur dibromide. Sulfur has 6. Bromines have 7 times 2 is 14, so I have 20 electrons. I start with sulfur, S. I draw a bond to each. I have used 4. I have 16 left. I place 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I fulfilled the octet on the outside. I have 4 left. 4 go on the central atom. Okay, I've used all my electrons. I will now do formal charge. Formal charge here is 7, comes from the bromine, and I count 1, 2, 3, 4, 5, 6, 7. And 7 times the 7 minus 7 is 0. This bromine it looks exactly the same. Sulfur brings in 6, and I count 1, 2, 3, 4, 5, 6, 6. 6 minus 6 is 0. All zeros with a molecule that has no charge, that is a very valid Lewis structure. When I take a look at this, I will count the number of domains. And so each of the single bonds is a domain, 1 and 2, plus lone pairs are a domain, 3, 4. I have 4 electron domains. When I have 4 electron domains, that is in a tetrahedral arrangement. Okay? And so the electron pair geometry is tetrahedral. But when I look at this and I look at tetrahedral, if you go to your list, a tetrahedral that has 2 non-bonding pairs is actually bent. Although I have written it this way, this angle looks like it's linear, but really the angle is 109.5 because the structure is based on a tetrahedral, which, because I have 1, 2, 3, 4 domains around that, and so I arbitrarily drew it to make it look like 180. I could have very simply drawn it differently and did this. The Lewis structure is no different, but that angle here looks like 90. It is neither 90 nor is it 180. It is 109.5 because, again, even in this structure, 1, 2, 3, 4 bonding pairs, 4 domains, create a tetrahedral, and in a tetrahedral, your angle is 109.5.